Hello. Thanks a lot for the invitation. I think this is on. Okay, it says it's on. Does it sound on?
Yeah.
So, yeah. This still says Columbia University. I just moved to the Gatsby unit at University College London. That will mean something to you if and only if you're in machine learning. So, what I'm talking about here is joint work with Morgane Austin. And Morgane is sitting there. Morgane, can you wave? Hello. Yeah. So Morgane was my student at Columbia and is now a postdoc with Christian and Jennifer over at Microsoft Research. Okay. And what I'm going to talk about is this. So I'm just going to throw a result at you, and then I'm going to spend the rest of the talk explaining that result. Yeah. So the setup is as follows. I have a random object x, and think of this as an infinitely large random structure, an infinitely large random graph, or an infinitely long random sequence, something like that. Yeah. And that random object is the distribution of this object. The distribution is invariant under the action of some group G. Yeah. So exchangeability is a special case of this. Yeah. If this is an exchangeable sequence, this here is a random sequence, and G is the group of all finitely supported permutations acting on the sequences of that, on the indices of that sequence. So I'm assuming that this random object is invariant under each element of that group transforming it in distribution. Yeah. And then I'm making an assumption on this group. So this group is always an infinite group. And it's not necessary, but for the purposes of this talk here, I will assume that it's countable. Yeah? We're only going to look at the countable case because it makes notation a lot easier. Yeah. So, and there's, now I'm going to pose a condition on this group, which is that it contains a sequence of finite sets that I call A1, A2, and so on, that satisfy a certain condition. We're going to look at that later. And I'm going to take a function that is integrable with respect to that random object. Okay. So then there's a result that Elon Lindenstrauss proved in 2001. This is the ergodic theorist Elon Lindenstrauss. That's the son of Lindenstrauss in the Johnson-Lindenstrauss lemma. And it says the following: if I compute.
Pretty famous in his own right.
Yeah, that's right. So, yeah. So when I told you I'm in machine learning, right? When I talk to machine learners, they know Lindenstrauss only as a Johnson-Lindenstrauss lemma, right? When I'm at a combinatorics place, then, I mean, I've heard Balázs Szegedy refer to this Lindenstrauss here as, to clarify who he is, as the famous Lindenstrauss.
So actually, neither of them like being known for the Johnson-Lindenstrauss lemma. Neither the one who did it nor the one who didn't.
Yeah. Okay. So in Balázs terms, the famous Lindenstrauss proved this in 2001. Yeah? So what it says is the following. I compute an average like this. Okay, so I'm going to take one of these finite sets. That is a finite set of transformations. I apply each of these transformations to x. So I draw one instance of x. Okay, one realization of my random graph, say. I apply a finite number of transformations to that, so I get a bunch of surrogate graphs. And I evaluate my function on each of these surrogates, and then average over that. If I do that, and then as n increases here, so as I make these sets of transformations larger and larger, as n increases, this converges to the conditional expectation of f given something that is the ergodic component. Yeah? Either you know what that is and this is all clear, or otherwise I will talk about it later. Okay? So, and that happens almost surely. So if you translate this into language of statistics or inference, then this is a law of large numbers. Lindenstrauss calls it a pointwise ergodic theorem because he's an ergodic theorist, but in the terms of the kind of topics that we discuss in this workshop, is maybe law of large numbers is more appropriate. Yeah. So I compute some form of sample average for using information I extract from a large random structure, and it converges to an expectation. Yeah? And the convergence is almost sure. Okay. So in the result I want to talk about is basically, if you think of this as a law of large numbers, then we have the corresponding central limit theorem for that. Yeah. So what this says is if this function here, which for the purposes of having a law of large numbers, I assume to be in L1, if that is even in L2, and if there's an additional condition that we call conditional mixing, then this average, yeah, so this guy here, this average, we know that that converges to this value. Yeah. The distance to that limit scales in a square root sense, just as in the central limit theorem, except that here this is not necessarily the square root of n, but the square root of the size of the set of transformations. Yeah. And that converges to a normal variable with a variance. This variance is in general a random variable. And that random variable is almost surely finite. And we can also give a specific form of that I have not written down here to save up on notation. But sorry.
Looks like it's not your.
So, okay. So, no, it's okay. It just needed a moment to recover. Okay. So, okay. So there's we have this here is a random asymptotic variance, and this random variable is independent of this one. Yeah? These two are independent. Okay. So I'm going to unclutter the slide a little bit and just focus on this result that we have. Yeah, everything here is the same. I just deleted stuff. And basically what I now want to do in the rest of the talk is explain, try to explain the conditions, the setup, and the conditions in the simplest possible terms. Yeah? And try to make it not like as non-technical as possible. So no, I'm not going to say anything about eta. No. Yeah. I may end up saying something accidentally about something that is not blue. Yeah. Okay. So I have to talk about a little bit about what invariance is or means, and then about this condition here, what we mean by conditional mixing. Then I want to give an intuition for this average, at least in the cases that typically arise, that we typically see in statistics, and what the ergodic component is. Yeah. Okay, so I first want to, let me start with symmetry, what I mean by symmetry, right? So that is this invariance under a group. So in proper terms, I call a random structure X symmetric if it is invariant under some infinite group of transformations, right? And the example that has come up yesterday, I think in Tamara's talk, is exchangeability. And the simplest case is an exchangeable sequence. So we have an infinite random sequence, right? And that's exchangeable if if specifically I have a transformation that is now a permutation, right? And the kind of permutations that I'm looking at are all finitely supported permutations of n. So all permutations of the natural numbers that change a finite but arbitrary number of elements. Yeah. So the definition of exchangeability doesn't change, right? So if the two groups are very different, right? This here is a group this group is countable. The group of all bijections is uncountable, and it's in group theoretic terms, it's a much wilder beast. Yeah. And just a term in what it means to be exchangeable, you come out with the same thing. So a sequence is exchangeable in this sense, invariant under the so-called finitary symmetric group, if and only if it is invariant under all bijections. But here, for when we compute these averages, then it makes a big difference. Yeah? So as soon as you come to anything that involves the notion of ergodicity, changes a lot as soon as you have that uncountable group. Okay, so examples of such symmetries include exchangeable sequences like this, right? Then exchangeable graphs, and all graphs generated from graphons are exchangeable graphs. Right? Then there's, like, more generally than graphs, you have so-called exchangeable arrays. So basically matrices that are exchangeable, or tensors, such like that. There are exchangeable partitions, on which Tamara has done a lot of work. Exchangeable random measures, and then there are things like homogeneous fragmentation processes and so on that also involve exchangeability. Another example of symmetry are stationary sequences and random fields. So in that case, if you have a random field on a grid, yeah, two-dimensional grid, then the group is not permutations anymore, it's shifts of the grid. Yeah? So the group, in that case, the grid is given by z2, z to the power of 2, right? And the group is also given by z to the power of 2. And then there are things like translation and rotation invariant fields that on the plane. In that case, the shift group is not countable anymore. It's an uncountable group. And we can also deal with uncountable groups, but again, I've left that out of the talk. Okay, so these are the kind of random objects that I'm interested in. And now for this estimation problem. So it's useful to think of this function f that I apply to my structure as a function that depends just on a small part of it. Yeah? So if I have a random field here, this is the example of a random field on the grid. So if I have a random field, I have at each grid point, I have a random variable. And now my function might depend only on a single one of these random variables, say at the origin. Yeah? So I have a function of that random field at the origin. And now I observe a part of the structure X that is, in general, is larger than just this little window here where F lives, but it's finite. Yeah? So I observe these 9 values here. That is my observed sample. The random field is infinitely large. Yeah? And the function just depends on this. And now what I want to do is I want to estimate the expectation of this function. Yeah? So something I might do is to say, okay, if I'm in the sequence case, right? Then, I mean, for IID sequences, what we do is, so if I take a statistic of an IID sequence, then my function would just depend on the first sequence value, right? And how do I estimate the expectations in an IID sequence? I will collect the function values at each entry of the sequence and then average over those. So can I do something similar here? Yeah? And in order to do that, I have to move the function over the grid. Yeah? And so that's what I'm doing here, right? I take this function, I move it over the grid and collect values. And the way that, I mean, a way to represent that is that I'm transforming the grid. I can think of this as moving this window, or alternatively, I can think of it as leaving the window in place and moving the grid under the window, right? And that is a transformation of the grid. So that's what I've done here. I've applied a downward shift to this x, and that effectively shifts the window upwards. Okay. So, and now I'm going to collect all transformations that I need in order to cover my sample, right? So I have like I've observed some small part of my structure, and I take all transformations that I need to move that window over every position in that sample, right? I collect those in the set AN here, right? And so we can roughly think of the finite set AN of transformations as all transformations that I need to cover a sample of size n. And then, since I have an infinite structure, if I want to cover that entire infinite structure, I need an infinite set of transformations, and that is my group. Yeah? So the group consists of all transformations that I need to cover an infinite sample. And that is why the group is always infinite. Yeah? I want to prove a law of large numbers or a central limit theorem. That's an asymptotic result. So I need some notion of asymptotics of infinity. Yeah? And the group is always infinite because that corresponds to infinite sample size. So, and now I define this estimator here. That estimator, when we look at this estimator again that I mentioned earlier, what that says is simply move the window over your sample and collect sample values, right? And then normalize it. That I have? No, they're not IID. They're not IID, but they do have the same. They do have the same expected value. Yeah. Yeah. Okay. So, for example, what my estimator would look like here on this right. I mean, the grid that we just looked at, very simply, that has 9 entries, right? So what we get here is the shifts upwards, downwards, and sideways, right? So we cover all these 9 points, and then we normalize by those 9 transformations. Okay. So, and so that is where we have invariance, and that is where this estimator here comes from. Right? Now, okay, and I mean, okay, let me just maybe add. So what Philippe just mentioned was that because I have invariance, the expected values of these guys here are the same at every location, right? And so intuitively, if you think of the basic law of large numbers for IID variables, right, then all these values that we collect, these function values that we collect at different entries, they are independent and they have the same expected value, right? So if we want to estimate an expected value, then we should certainly assume at least that those expected values would be the same at all positions that we're collecting from, right? And then additionally, we have independence. So now the question is, or what Lindenstrauss result says is, even if you don't have independence, you can still get convergence if your group is nice enough. Yeah? And I think it's really quite remarkable that, I mean, I've been working on this for a while now, and it keeps boggling my mind that you can formulate that purely as a condition on the group. Yeah? It's really purely a condition on the group. Yeah. Yeah, you can, I mean, if you just look at the exchangeable case actually, then you can just prove that by a very simple martingale argument. Yeah, that results, so the exchangeable version, the symmetric group version of Lindenstrauss result is so simple that I used to pose it in qualification exams for our PhD students, where you can't invest more than half an hour, right? And all they knew was martingales. That was the only tool they had. Yeah. And I'd say about 60-70% of them got it. Yeah. But the proof in the general case is very, very hard. Yeah. So we could prove the central limit theorem, but we could not have proven that. Or I mean, actually, I'm not so sure. Maybe Morgan could. I could not have proven that. Yeah. Okay. So now for this condition on the group, that condition is called amenability. That is not by coincidence the same word that Ahmed used earlier in his talk. Yeah, those two are very closely related. This condition here is a condition on the group. The condition he mentioned is a condition on graphs, but it's actually derived from the condition on the group. Yeah. So, but to motivate it in this context here, I want my average over these transformations to be a valid estimator of the expectation, right? And I know that because I have invariance, that if I take some fixed transformation I call psi here, it's one transformation in my group, I fix that, then f of x and f of psi x have the same expectation, right? Now, let's say this is a valid estimator, and let's just not think about what exactly I mean by valid, right? But somehow this converges to this, yeah? Then as n gets large, the value of this must be approximately this, right? And at the same time, if I now just apply the same estimator to the function f times psi, that is also, I mean, if this function is L2, then this is going to be L2, yeah? So if I apply that to that function, then I get an estimator that looks like this, right? So I apply my transformation here, phi, to f compose psi, and then I can pull psi out and first apply to this entire set of transformations. Right? So that estimator must be approximately this, and these two are the same, so that means that this guy and this guy must be the same, right? And now I can think about how can I ensure that those two here are approximately identical. I could either pose some form of conditions on f and x, but I really don't want to do that, right? Because I'm trying to develop a tool here that I can apply to a problem. If possible, I would like to pose conditions on my tool, not on the problem, right? So what I want to do is pose conditions on everything but f and x, and that means I will have to pose a condition on the set A. Yeah? And so if we want to ensure that Fn is approximately the same as f compose psi n, right, the estimator, then that means that the set in this estimator here and the set of transformations we use in this estimator and the set of transformations we use in this estimator have to be approximately the same. And that means an and psi applied to every transformation in an have to be approximately the same set. And that is exactly what this condition says here, right? It says if I apply psi to an, then if n is large enough, basically an doesn't move, right? It hardly moves. So I measure the similarity here in the most straightforward way by just taking intersection. And I don't invent a metric or something. I just take an intersection and measure size. Right? Okay. So if a group if a sequence of sets that satisfy this condition exists in the group, then the group is called amenable. Yeah? And if you, more generally, in the case, I mentioned that we can not only do this for countable groups. If we have uncountable groups, what we need is we need the group to be locally compact and second countable. It needs to have Haar measure. And then these sets, instead of finite sets, these become compact. And here the individual single transformation psi is substituted by a compact set. Okay, but so that is called an amenable group. And examples of amenable groups are the finitary symmetric group that I mentioned before, right? Then the shifts on the grid, and then there are various others, right? And there's also so if you have an amenable graph, then you can translate that into statements about the automorphism group of the graph, right? So basically, I think in your case you have an amenable graph and you have unimodularity, so you basically have invariance under some form of amenable group there, I suppose, right? But I
The other group we can consider the Cayley graph. The Cayley graph would be amenable in my definition.
yeah. Okay. So that gives us this condition, right? So we have invariance, we have this condition, we have this estimator. Now we have to look at what conditional mixing means and what the ergodic component means. Yeah? And the ergodic component, that is the hardest part. Yeah? That is to explain if you're not familiar with that kind of literature. And so I'm going to do it heuristically. So if you have a group that is locally compact and second countable, then you can and you look at the set of all probability distributions that are invariant under that group. Say all distributions of exchangeable graphs. Yeah? Then what you can show is that first of all the set of invariance distributions is convex. Yeah, that's trivial. You can just figure that out in 2 lines. Yeah? But then you can show that the extreme points of the set are measures that have a certain property. So these are the so-called ergodic measures. Yeah? And I'm just going to illustrate that by example what these ergodic measures are in cases that you might be familiar with. So if you have an exchangeable sequence that's indexed by sequence indexed by the natural numbers, it's exchangeable, then the ergodic distributions are the IID distributions. That is Diffie-Netti's theorem. Yeah? Or more precisely, it's the Hewitt-Savage 0-1 law. So if you have an exchangeable graph, then the ergodic measures are exactly those distributions that are defined by graphons. Yeah. If you have an exchangeable partition, so the kind of object that Tamer has worked on a lot, exchangeable partition of the natural numbers, then the ergodic measures are given by partitions of are indexed by partitions of the unit interval, countable partitions of the unit interval, and those distributions are often called paint box distributions. That terminology is due to John Kingman. Then if you have, say, a discrete time Markov chain and the invariance is stationary, then you have irreducible aperiodic chains here and so on. Yeah. If you are a statistician or in machine learning, then there is a Bayesian versus frequentist interpretation of this. Basically, if you build statistical models of invariant structures, then a statistical model is a set of probability measures, right? The natural choice for that set of probability measures will be a subset of the ergodic measures. And this statement here says that the way to generate that every invariant distribution can be generated by selecting an ergodic one at random and then drawing from the ergodic one. Yeah? So we have a convex set here. The extreme points are the ergodic measures. And that means getting into the interior of the set is mixing over those ergodic measures. Right? So select an ergodic. To generate an invariant distribution, you select one ergodic measure at random and then draw from that ergodic measure. And so the frequentist interpretation would be, or the kind of frequentist approach here would be, you select your model as a subset of the ergodic measures. Yeah? The Bayesian version would be, you put a prior on those ergodic measures, and that gets you into the interior of that set. So in terms of exchangeable graphs, for instance, if you build the frequentist approach would be you define a statistical model that consists of, whose elements are indexed by graphons. Yeah? You can do that in a parametric or a non-parametric way as you wish. A Bayesian version would be you put a prior on graphons. Yeah? Okay. And what we have in our result is we get, or in Lindenstrauss result, right, we get convergence to this conditional expectation of f of x, given the ergodic component. Yeah? And what that means is you recover information, you can recover information about the ergodic component. Yeah? Here, any invariant distribution can be sampled by selecting ergodic component at random and then drawing from it. That means somebody just hands me the result. They don't tell me which ergodic component they have drawn, right? This converges to the value of this under the ergodic component. So I can recover the ergodic component from data. Yeah? So I mean, I'm a computer science. In computer science terms, conditioning here is a feature, not a bug. Yeah, Christian.
So in physics, ergodicity has sort of some intuitive meaning of things mixing or so. If you have the sort of ergodicity of the system means something, sort of that thermodynamics makes sense and things like that. Can you tell us a little, at least intuitively,
Yeah.
what
So
it has to do with it, and which one is sort of, because it's called ergodic, it's normally called extremal, so there must be reason you don't say extremal, but you say ergodic.
Yeah. So in the simple so in this setup, the two are absolutely equivalent, extremal and ergodic. Yeah? If your group is not nice enough, then they may not be. Yeah? The statistical physics comparison would be, so in an ideal gas, your particles, you can think of your particles as approximately independent, right? So they are random variables given by 3 location variables and 3 momentum variables, right? They are approximately independent, so you can think of them as IID. You have a very large system of IID variables, right? And the size is approximately 10 to the 23rd, right? The thermodynamic limit. And so now the fact that macroscopic observables, temperature, pressure, and so on, that those are stable in an ideal gas, right? That the temperature in a gas that has no outside influences doesn't just fluctuate wildly, even though it's the outcome of randomness, is because the system is large enough that you're basically in an asymptotic regime. Everything behaves like a limit. It behaves like this limit here. And the reason why it behaves like that limit is because 10 to the 23rd is so large that if you have IID variables and a central limit theorem and square root convergence, you're behaving as if you're in the limit, right? And that is something that statistical physicists know, right? I mean, on page 2 of Parisi's book or something, you will find that square root convergence, right? And basically what our result, with our central limit theorem, you can reason about if my system is not IID variables, if those particles are not IID, they are dependent, but they satisfy some form of transformation invariance, then how large is large, right? Is 10 to the 23, is that large enough or not, right? So, I mean, you need to know what constants are in that world. But okay, I think I should go on. Okay. So, just want to, again, so I want to say something about this conditional mixing condition, what that means. And again, I'm going to sidestep a precise definition because setting up the notation for that would be a talk in its own. Yeah. But the intuition is very simple. So mixing, recall that what mixing means in a discrete time stochastic process, right? It basically says there are like various variations of this definition, but basically it says if I take some time k, some index k, and look at the value of the process at that index, and then I take the tail of the process further out, right? So I have my infinite sequence, I look at the value at some point, and then at the value further down the sequence. I ask how dependent are those, right? How dependent is this one value and the tail out here? And how does that dependence behave as I shift out the tail, as I push them further and further apart? And mixing basically means if I make n large enough, so if I make the distance between this and this tail large enough, then they're approximately independent. Yeah? So in conditional mixing simply means that they are approximately conditionally independent. Yeah? And conditional on what? On the ergodic component. Yeah? So the other difference is that we're not necessarily dealing with sequences and shifts. We're dealing with these invariances under groups. And so the condition that we actually need looks like this. We need 2 elements of the group. Yeah? So instead of having one index here, we need to look at 2 elements of the group, as it turns out. We look at the function values at the respective surrogate structures here. And we ask that this pair behaves in a certain way with respect to these values here for all transformations in some set M. Okay? And the way we want it to behave is that if this set is far away from phi 1 and phi 2, then conditionally on the ergodic component, those should be approximately independent. Yeah? And so this conditional mixing is substantially weaker than mixing. So it's really a good thing that we only need the conditional mixing. For instance, in the case of exchangeability, even in an exchangeable sequence need not be mixing, but it's always conditionally mixing. Yeah. Yeah.
So what is far away?
Yeah. So far away, in order to measure what far away is, you need a distance on this group, right? So we need a metric group, but the group is locally compact and second countable for any of this to work at all. And so you always have a metric on the group that metrises the topology. And that metric, you can always make that metric left invariant. Yeah?
So why you take 2 elements, not 1?
Yeah. It's a little technical, but we need 2 elements. And we need like an arbitrary set here. Yeah? So instead of the tail here, that's a very specific set, right? But we need to make this has to hold for arbitrary sets n. So if we take two elements in any set that is just far away enough, so basically think of it as we take these two and we put a ball of some radius around it. Anything that is outside that ball must satisfy this condition.
And approximately is
Approximately is exactly in the same sense as in mixing, like in stochastic processes, right? So you have, you compare, for two events A and B, you compare this to this. Yeah? So that's exactly like mixing in basic.
so it will be
mathematics.
that for all epsilon there is some distance such that if m is far than that distance from both phi1 and phi2,
Yeah.
this is smaller than epsilon.
Exactly.
And this should be uniform if phi1 and phi2 was the choice of m, or
No.
does the epsilon, can it depend on phi1 and phi2?
Um,
So is it sort of an epsilon phi1, phi2 delta argument, or is it an epsilon delta?
yeah. I should know this from the top of my head. I'm going to ask Morgan. Morgan, does the epsilon depend on phi1 and phi2 or not? Is it uniform?
I couldn't hear his question.
Okay, let's take it offline. Okay,
I'm sorry.
let's take it offline because I don't have a lot of time left. Yeah. Okay. Okay. So. So now we have collected these, yeah, and I want to say a few words about specific cases, yeah. So if we have an exchangeable sequence, so exchangeability means the group acts on the index set of the sequence. Then let's say I take a specific permutation, right? And the way I define my function in this case might be that it just is some function of the first entry. Right? This is just the simplest thing. So basically what I'm doing now is I'm just getting back the basic law of large numbers, the basic central limit theorem. So I apply my function here. Think of this gray thing as a little window where the domain of this function, right? And in the case of the basic central limit theorem in law of large numbers in statistical probability, I would take this window and shift it along the sequence and collect those values, right? And now what I'm doing is I apply my permutation, and that way I pull some element of the sequence to the first location here, and I collect that value. Okay. And now in the central limit theorem or law of large numbers, the way this average looks is, so that is the way I had written it down before, right? The general form. Now I plug in the symmetric group here. Okay, so I look at all permutations of the first n elements of the sequence. And now this here, the size of this group, I have to normalize by the size of the group, and that is n factorial. Right? And but the way that we scale in the central limit theorem is not by n factorial, it's by 1 over n. Right? And that is because if I just look at the first value here, so there's n factorial permutations of n numbers, but there's n minus 1 factorial of them where the first value, the particular entry will show up in the first position, right? And so that we get cancellation, and that effectively leads to 1 over n here in the normalization and square root of n scaling in the central limit theorem instead of square root of n factorial scaling. So there's a cancellation going on there. So, and then we just recover the central limit theorem and the law of large numbers as usual. Another example, yeah?
You could use the shift here to include these.
Exactly. So, there is something that we haven't made precise yet, but basically what we believe is going on is that inside the group you have some subgroup that is basically that is responsible for mixing, and that is effectively going to give you your scale.
That's gonna be.
That is what effectively determines the scaling. Yeah, it just happens here. I mean, it's easy to see that this cancels out. It's not so easy to make precise what I just said. So, yeah, that's true. That's true. No, what I'm trying to show here is like why does exchangeability reduce to this case, right? And exchangeability in general, even when you can't use shifts, like in exchangeable graphs, you have always some cancellation going on here. And this is the case where it's easiest to see why things cancel. So in an exchangeable graph, you would have, say, a graph like this, right? And my window is here on the first n vertices, or the first 3 vertices, say. So I now take a function that, say, is the indicator of a triangle or something like that, right? So it's something that depends on subgraphs of size 3. So I look at the first 3 vertices, and then I apply some permutation, and it takes some other vertices and pulls it to the first 3, right? And here I graph that as like this. So now the window would depend on these guys here. Okay? And so in this case here, in the original graph, the subgraph on the first 3 vertices looks like this. So it's a path of length 2. And in this case here, after applying the permutation, the subgraph on the first 3 vertices is like an isolated vertex and the path of length 1. Right? And then the central limit theorem looks like this. The probability, this average here, again, then there's the ergodic component. So this is now determined by a graph one. This is under the true graph one, if you will, that generated the graph. And then you can see here that the normalization looks now a little different because we have triangles and we again get square root of n scaling. Yeah. So more generally in the exchangeable case, something that's interesting in the exchangeable case, that is basically the mixing condition vanishes. Yeah, you're always mixing. The only condition that you need is that this function is not completely insane. And that is given by this condition here. And then you always have a central limit theorem like this. I've written it as square root of n factorial and then 1 over n factorial here, but you will always see some form of cancellation here. That's just something that happens with exchangeability, that this will end up being square root of n scaling. And so in addition to the central limit theorem, we can also quantify what the Wasserstein distance between this here and this limiting normal variable is. And that is a Barry-Esseen bound, if you're familiar with that term. Yeah? So in addition to the central limit theorems, we have various generalizations of those. We also have Barry-Esseen bounds. Yeah, I just left that out of the talk. Okay. My time is up, so I'm going to skip the rest. And I'm just going to ask you to look at this here for a moment, right? So basically, what we have here is that symmetry yields convergence. So a short way of, I mean, in a nutshell, basically what this says is if you take the basic limit theorems of statistics and probability that hold for IID variables, and instead of IID, you have a symmetry condition, then they may still hold. Yeah? And basically if we have symmetry and a reasonable topology on the group, then we get representation theorems. So those are things like De Finetti's theorem, yeah, or the Aldous-Huber theorem. If we add a function that has a first moment and amenability, so this condition on the group, then we get Lindenstrauss theorem, so we have law of large numbers. If we add a second moment and a mixing condition, then we get a central limit theorem. Yeah? And the other thing that I briefly want to mention is that, so when we look at these other types of symmetries, for exchangeability, we have, so many of you will have seen De Finetti's theorem, the Aldous-Huber theorem, maybe Kingman-Painbock theorem. What these all have in common is that for these ergodic components, we have a very concise representation that we can sample from, like a graphon, for instance, or a paint box, right? These kind of limit objects are in the probability literature on this topic sometimes called codings. Olaf Kallenberg called them a coding. And it seems that the existence of these codings is something that is specific to exchangeability, and that is something that I find really fascinating. I don't know of a single example where we have, so the kind of general structure of Diffie-Nelly's theorem, that we have these extremal measures in this convex set, that always holds for all kinds of symmetries that under reasonable conditions, but that these extremal measures are represented by these concise limiting representations. That is something that we seem only to have in the exchangeable case. Okay, that's it for me. Thanks very much.